What happens when you replace a hydrogen with a substituent on a chair conformation? When one substituent is attached, it can be located in either the axial position or the equatorial position. And this is because the chair conformation can flip at room temperature. We call that ring flip, and this is happening by rotation of all the carbon-carbon bonds in the ring. Upon the chair flip, the axial positions become equatorial and the equatorial position becomes axial. So let's look at this model. This is the chair conformation where the substituent is in the axial position. Now upon chair flip, so this is chair flip. Now the position becomes the equatorial. The one that was axial becomes the equatorial upon the chair flip. Now let's draw the two chair conformations that are converting to one another upon ring flip. So the first one, we already tried to draw it on a paper. We need 3 sets of parallel lines. So this is my first set. They are pointing to the left kind of. And then I have my longer lines and the shorter lines. Now to show the chair flip, instead of drawing these 2 lines pointing to the basically left, I need to draw them pointing to the right. So in the parallel format, all right, now I have basically my longer lines. They are coming here, and this is my shorter line. Okay, and this is the chair flip. So for example, if I have a substituent right here in the axial position, let me number the carbons. So it is carbon 1, 2, 3, 5, 6. So this position, that was the carbon 1 that was pointing up, now it is pointing down. So it's going to be 1, 2, 3, 4, 5, and 6. And the chlorine becomes in the equatorial position. Chair flip is a conversion of one chair conformation to the other. And upon the chair flip, all the axial positions move to equatorial and all the equatorial positions move to axial. When you have one substituent on a cyclohexane, the favored conformation is when the substituent is in the equatorial position. So at room temperature, we can find 5% of this conformation where the methyl is in the axial position and 95% of this conformation where the methyl is in the equatorial position. Now, why is that? When we have a substituent in the axial position, this causes steric interactions in the molecules. So meaning that this substituent would have steric interactions with these hydrogens that are 3 carbons away from that. And we call that kind of interactions 1,3 diaxial interaction, which destabilizes the conformation. And we call that 1,3 diaxial because if the substituent is on carbon 1, it has interaction with 2 hydrogens that are 3 carbons away from that. So it is 1,3 diaxial interaction. Upon chair flip, the group that is in the axial position goes to the equatorial position. Therefore, that 1,3 diaxial interaction will go away, which makes the conformation more stable. So when you have monosubstituted cyclohexane, that substituent always prefers to be in the equatorial position. Now let's make a note of that. So when you have monosubstituted cyclohexane, substituent always prefers equatorial position. Now, what if we have more than one substituent connected to the cyclohexane? We have an example here where chlorine and methyl group attached to the cyclohexane. So if I number this carbon as carbon 1, methyl is connected to carbon number 2. So chlorine is shown in wedge bond and methyl is shown in dash bond, meaning that they both pointing towards opposite directions. So I made the model of this structure. Okay, this is the cyclohexane and this is the chair conformation. So this is the chlorine and this one is methyl. Chlorine is in wedge, so means that it is basically up the plane of the ring. So if you imagine there is a plane passing through the ring, so this is up, and methyl is in dash, so it is going down the plane of the ring. Both of them are pointing into opposite directions. So chlorine here is in the axial position and methyl is also in the axial position. Okay. Now the chair flip can happen, and upon chair flip, okay, so now both of these groups are in the equatorial position. So if I rotate the ring, chlorine is still up comparing to the plane of the ring, and methyl is pointing down. So chlorine is up and it can be axial or equatorial. So in this conformation, chlorine is in the equatorial position, and in the other conformation, chlorine was in the axial position. So being up or down doesn't do anything with axial or equatorial. A group can be axial and it can be equatorial and be up the plane of the ring. Now, between these two conformations, this one, where the chlorine and methyl, both of them are in the axial position, and this conformation, where both of them are in the equatorial position, so between these two, which one is more stable? Now, here is the rule. We always prefer the group to be in the equatorial position, because if they are in the axial position, they would have 1,3 diaxial steric interaction with the hydrogens. So therefore, we always prefer the group to be in the equatorial position if it is possible for them. So to draw these conformations, what you can do, you can make a model as I did here and draw them on a paper as you see them. Or if you don't have a model, we have a few rules that we need to follow to draw these molecules on a paper. To draw the chair conformation on a paper, the first step is to number all the carbons in the ring. So I already gave number 1 and 2. This is 3, 4, 5, and 6. You can start number 1 at any of the carbons. It doesn't matter which one. As long as the numbers go clockwise, it should be fine. Then you need to draw the chair conformation and number the chair conformation. So I personally prefer to give number 1 to this carbon, and then I need to complete the numbering moving clockwise. And the reason behind it is that we have a chart here that can help us with defining axial and equatorial positions. I'm going to talk about that later. But to use this chart, the numbering pattern should be the same as what I did here. Otherwise, you will get an incorrect structure for your chair conformation. Now, let's do the chair flip and number the new chair conformation that is forming due to chair flip. Upon chair flip, carbon number 1, which was up, comes down. So this is going to be 1, 2, 3, 4, 5, and 6. Be very careful about your numbering. Then we need to look at chlorine. So chlorine is in wedge, and wedge bond means up, and it is on carbon 1. And up position in carbon 1 is right here in the axial position. Methyl is in dash, and it is connected to carbon 2, and dash in carbon 2 means down, which is axial position. Okay, so both of these groups are pointing towards different directions, and here they are pointing towards different directions. Now both of these groups are in the axial position. So to draw the next chair conformation, you need to do chair flip, and upon chair flip, the axial positions becomes equatorial positions. So chlorine, carbon 1 is now in the equatorial position, and methyl in carbon 1 is now in the equatorial position. So remember to draw equatorial, you need to draw a bond that is towards this tip. Now, which one is more stable? The second structure is more stable because both groups are in the equatorial positions and they don't have any 1,3 diaxial interactions. So both therefore this one is more stable. There is a chart that we can fill it out together. This chart can be helpful while putting the groups on a cyclohexane ring without using a model. So you can draw a chair conformation and number the chair conformation in order that I did. So this is carbon 1, 2, 3, 4, 5, and 6. Now, for carbon 1, 3, and 5, the up position is the axial position. Okay, so the up is axial, therefore down position should be equatorial. So if you see anything in wedge and it is on carbon 1, 3, or 5, you need to put it in the axial position while drawing the cyclohexane. And for carbon 2, 4, and 6, 2, 4, and 6, the down position is the axial position on a ring. Okay, and the opposite of that should be equatorial. So a good example here. This is carbon 1 and it is in wedge. I know that wedge means up. So for carbon 1, up is axial. Up is axial. For carbon 2, it is in dash. I know that dash means down. So carbon 2 down is axial. So I can put it in the axial position. So we need to draw both chair conformations for this molecule and decide which one is more stable. The first step is to number all the carbons in the ring. So I start with this one. I give number 1 to this carbon. The order of numbering on this ring, it doesn't matter. You can give number 1 to any of these carbons in the ring. However, if you want to use this chart, the order of numbering in the chair conformation and the chair flip is important. So I start with this one. This is my carbon number 1. And upon chair flip, this is carbon 1, 2, 3, and 6. Now, if you look at chlorine, chlorine is in veg and it is connected to carbon number 1. So veg means up. Carbon number 1, it should be in the axial position. And then we have on carbon number 3, we have hydroxy group attached. It's in veg. Veg means up. Carbon 3 up. That one should also be in the axial position. Okay. Now both of these groups are in the axial positions. To draw the chair flip conformation, both of them will go to equatorial positions. So upon chair flip, the axial positions becomes equatorial positions. So chlorine now is in equatorial. Hydroxy is also in the equatorial. Now which one is more stable? Obviously the second one, because both groups are in the equatorial position. So they don't have any 1,3 diaxial interaction as these two groups have here. So they are completely separated from one another. However, here they have 1,3 diaxial interaction. So the second one is more stable. Both are in equatorial positions. So this structure or this conformation is more stable. Okay, so for this structure, again, we need to draw both conformations and decide which one is more stable. So let's draw the chair conformations. We start by drawing two parallel lines. Okay, so this is one chair conformation, and let's draw the chair flip as well. Okay, all right. Then we need to number all the carbons in the ring. So you can start with methyl or ethyl or any other carbons. I start with ethyl. So this is 1, 2, 3, 4, 5, and 6. And then we need to number all of these carbons. So the order of numbering in the chair conformation matters if you want to use, again, this chart. If you don't, the order does not matter. As long as you identify the axial and equatorial position and know which one is up, which one is down, you're good. 4, 5, and 6. Now to carbon 1, we have ethyl group attached. Ethyl is in veg, which means up. So up, carbon 1 is axial. Okay, so this is ethyl. And to carbon 3, I have methyl group attached. It is in dash. So carbon 3 dash means down, and it should be in equatorial position. So the equatorial position is right here for methyl. Now upon chair flip, the equatorial becomes axial and axial becomes equatorial. So ethyl is in the axial position. It should be in the equatorial after the chair flip. And methyl is in the equatorial position, so it should be axial after the chair flip. The axial is right here on carbon 3. Now, which one is more stable? So here we have ethyl group located in the axial position and methyl is in the equatorial position, and in the second conformation, ethyl is in the equatorial position and methyl is in the axial position. Now, which one is more stable? Now, which conformation is the more stable one? In the first one, the ethyl is in the axial position and methyl is in the equatorial. In the second one, ethyl is in the equatorial and methyl is in the axial position. To answer this question, we need to know a concept which we call that A values. So A values are used to determine the most stable orientation of the atom in the molecule. What you need to know about the A values is this conclusion, which says that groups with higher A values tends to be in the equatorial position. Here is the table of A values. So the larger the atom, the higher the A value would be. So this group, this is the tertiary butyl group. It has the highest A values in this table. And after that, we have phenyl substituent. So it gets the A value of 3. Now, you don't need to know these numbers. What you need to know is the equatorial position preference for all of these substituents. And that order would be, so equatorial, so this order is based on the A values. And based on that, tertiary butyl prefers to be in the equatorial position more than the other substituent in this table. So the tertiary butyl, if you remember the chicken finger one, it's this group. After that, we have phenyl substituent, which is the benzene ring. When it is a substituent, we call that phenyl. After that is isopropyl. You know the structure of isopropyl, 3 carbon that is attached from the second carbon to the chain. Then we have ethyl, CH2, CH3, methyl, which is CH3. We have hydroxy. Then we have methoxy. So methoxy is OCH3. This is methoxy. After that, we have iodine, chlorine, and bromine. They are almost the same. And after that, we have fluorine. So if you look at this trend, halogens, they have the lowest A values in this table. So if you have halogens and basically alkyl substituents, always alkyl substituents prefers to be in the equatorial position. Now, to answer the question that which conformation is more stable here, so according to this trend, ethyl substituent always prefers to be in the equatorial position more than methyl substituent. Therefore, this conformation is the more stable one because the ethyl substituent is in the equatorial position here. Now let's look at the practice problem here. So one more practice. Okay. So we need to draw both conformations for this molecule and decide which one is more stable. So the first step is to number all the carbons. Okay, and then draw the chair conformations. Okay, then I need to draw the chair flip. Okay, then I need to number all the carbons. The numbering, the order is important. Pay attention. I can write, basically draw the table that we worked on one more time. C1, C3, C5. They are up axial and down equatorial. C6, equatorial and axial. So I start with tertiary butyl group. So the tertiary butyl group is in the wedge, meaning that it's up and it is on carbon 1, so it should be in the axial position. I draw that in the axial position. Then the next group is on carbon 2, which is in the dash, and it's a methyl. Dash means down on carbon 2, so it should be in the axial position. Okay. And then I have iodine on carbon 4. It is in wedge, so the wedge means up. Carbon 4 should be in equatorial position. Okay, now let's do the chair flip and draw the conformation. So upon chair flip, the axial tertiary butyl will be equatorial. The axial methyl will be equatorial as well. Okay. And the equatorial iodine will be axial. Now, in the first conformation, tertiary butyl, and let me number. Okay, so tertiary butyl and methyl, they are in the axial. However, iodine is in the equatorial. In the next one, I have tertiary butyl in the equatorial and methyl in the equatorial. And in the axial, we have iodine. So if you look at the A values, which one is preferred to be in the equatorial? Obviously, tertiary butyl, and after that methyl, and then iodine. So we prefer to have tertiary butyl and methyl in the equatorial position rather than iodine in the equatorial position. Therefore, the second structure would be more stable because the tertiary butyl and methyl, both of them are in the equatorial position according to the equatorial position preference order. Let's look at another example here. Sometimes you may see a Newman projection and the question is asking you to convert it to the chair conformation. So one way is to make the model and rotate the molecule in a space to see a chair conformation and draw it as you can see it. However, if you don't want to use a model, there is an easy way to do it. So the very first step is to number the Newman projection. So be aware that this numbering is different from the numbering pattern that I used in the previous video. That pattern was for identification. So both numbering patterns are correct. However, if you want to use these charts that we developed and the method that we practiced right here, you need to number the Newman projection as I do right now. So based on that, this carbon would be carbon number 1. The back carbon that we don't show it is 2. The front one is 3. This one is 4. We have 5, and back of that is carbon number 6. Now, when you look at the Newman projection, these substituents that they are pointing up, they are also up in the chair conformation. So they are up here. And these substituents that are pointing down, they are also down in the chair conformation. Okay. Now, to convert the Newman projection to the chair conformation, what I suggest you to do is to first draw the cyclohexane in a planar format, in a ring format. And then we can convert the ring to the chair conformation as we did previously. So this is the cyclohexane. Then you need to number this ring. You can start putting number 1 at any of the carbons. It doesn't matter which one, but be aware that it should be clockwise as we numbered the Newman projection clockwise. So this is 1. I start 1 with that carbon. 4, 5, and 6. Now to carbon 1, we have hydrogens attached, so we don't show them. To carbon 2, which is the back of carbon 3, we have also a hydrogen and hydrogen attached, so we don't show hydrogens. To carbon 3, we have hydrogen and methyl attached. That methyl is pointed downward, so we need to draw it as a dash connected to carbon number 3. To carbon number 4, we have 2 hydrogens attached. We don't show them. Carbon number 5, hydrogen and hydrogen attached. We don't show them. And to the back carbon, which is carbon number 6, we have cyano and hydrogen attached. So this group, cyano group, is pointing up. So we show that with wedge bond in the cyclohexane ring. Now from here, we can use the chart that we developed and draw both chair conformations. So first step is to draw the chair conformation. So we are gonna draw the chair. Okay, now let's number 1, 2, 3, 5, and 6. So to carbon number 3, we have methyl group attached, which is going down. So carbon 3 down is equatorial. This is equatorial. And to carbon number 6, we have cyano group attached, which is coming up, and it should be equatorial. Show equatorial this way on carbon 6. Then we can draw the chair flip. So draw a chair flip. Okay, so upon chair flip, that would be carbon 1, 2, 4, 5, and 6. Now upon chair flip, the methyl, which was equatorial, becomes axial, and cyano was also equatorial, so that becomes axial. So the axial would be right here, and the cyanoaxial on carbon number 6. So which one is more stable? Obviously this conformation, because both groups are in the equatorial position. So this is more stable or lower in energy. So the more stable, the lower the energy would be. Cis and trans stereoisomerism. We can call the groups depending on positioning to one another either cis or trans. And these occur when there are only two groups present in the molecule. If there is one or more than two, we cannot use this terminology. As I mentioned, cis and trans, they are stereoisomers to one another. We are going to learn about the stereoisomers in chapter 5. However, for now, we are just focusing on the name and the terminology. When two groups are spatially pointing at the same direction, we call the molecule a cis isomer. So for example, here, these two methyls, they are on the same side of the ring, so this is the cis isomer. When two groups are pointing in opposite direction, so for example here, two methyl groups, they are in opposite sides of the ring, we call that trans isomer. We can show cis and trans using wedge and dash bonds as well. So to show the cis here, I can use two wedge bonds, which shows that both of them are pointing into same direction. You can use dash bonds as well. And to show the trans, I can use one wedge and the other one dash. Now to name these molecules, the naming is similar to what you learned before. So you need to name the parent chain and name the substituent, their position and locations. After naming the molecule, what you need to do, you need to put the prefix cis or trans before the name of the molecule to show their spatial relationship. So the first molecule, this is the parent chain, is cyclohexane. And if I number the parent chain, this one should be 1, 2. I have two methyls, so dimethyl cyclohexane. Now to show that the two methyls are cis to one another, I put the word cis, the prefix cis before the name. And for the other one, the name is the same. However, I need to use the prefix trans to show that two methyls are trans to one another.